check out this restaurant, for example, then having some kind of certainty or uncertainty, mostly uncertainty, can be really helpful to reinforce your recommendations, or you make your recommendations more accurate, your predictions as well. So that's really can be really useful, but the devil is again in the details, right? So let's move to Jupyter Notebook. Right. Okay, so basically the way we start with just this very basic notion, what we're doing is we're putting weights over our so putting distributions over weights of the neural network basically, and adjusting them or intuitively updating them then gives us the final result in the end, which will then be our posterior. And I mean, this basically just describes base formula in a sense. Then again, we are always faced with these very sampling heavy things, and also with, as I'll explain in a bit and also show a bit, is you can end up with neural networks where you put in weights, but the inference problem is not really tractable. And that basically means that you don't really, you either need to look for a way to transform your problem into a problem which is then more tractable, or for one of the various inference algorithms you have at your disposal, or you have to basically abandon it. That's the other option. Okay, so main downside, of course, computational cost. That's always with probabilistic programming or like Bayesian inference overall, and also with these Bayesian networks, it's always computational cost, which is the main constraint. So I'm not sure if that still works. Let's just quickly get it running. That should be done in a second. So again, as kind of touched upon yesterday, in here, we'll probably mostly be using, okay, let's see. In here, we'll mostly be using the reverse diff backend because that's more stable. So that's also all right. So then we'll move to our first neural network, which is basically just at this point you just generate artificial data, and then we just visualize it for now. Pretty simple data, nothing too special here, I think. And now let's start constructing some neural networks, basically. So we transform. So basically, you have to unpack. So you have some level of abstraction in there to unpack the weights that are always given to your network, especially when the inference routine is running. So in here, you basically always have to specify the special function which unpacks the whole parameter vector. And then you have the forward function, basically takes in this abstract vector and then unpacks it into the individual variables and puts the individual variables into the network and then runs. So we didn't really see much of the flux syntax yesterday. So flux is so far the most prevalent machine learning system inside of Julia. In terms of syntax, it can be kind of compared to what you would usually expect from JAX, for example. So more of a functional syntax where both of them kind of define the functionality up front inside of your let's say cell or inside of your network, and then at the end you return it through a chain, or in tracks it would be something like a serial operator, which then basically just attaches all the different layers to each other and then basically constructs a network from that. I think PyTorch has a similar functionality. I'm not too sure about TensorFlow, but it's fairly straightforward. So basically, you just specify your layers, and then they are attached to each other, and it's basically just like putting Lego bricks on top of each other. So now this is where the Bayesian neural network stuff comes in, basically. So you define it again as a Turing model, so as a probabilistic model, and then we have our prior, which is the most very normal in this case. And now we say, okay, we want to calculate our predictions. So let's throw in XS, our data, and then the parameters which we just sampled from our prior. And so with that, we basically define our probabilistic model. And then we can basically do inference on that with exactly the same way like we did yesterday, actually. Still basically just sampling, but our model is slightly different now. This is the only, so this is already showing some of the advantages that you have here, because basically it doesn't matter to a probabilistic programming system if it's a tiny model or if it's a Bayesian neural network. It will always try to kind of capture it, but of course the inference problem is it's a lot harder here than it would be in one of these small toy problems from yesterday. Yeah, so in here, you usually use either NUTS, so the no U-turn sampler, or HMC, because they tend to be the most stable ones, especially if you have an unstable support. There will be an unstable support example later. You will really see that you can try multiple times, but it doesn't mean that you reliably converge, which is not that great. So now, what have we done now? So basically we've done the inference, just like yesterday, basically, and stored everything in the chain, so CH. And in here, we basically extracted the weights and the bias. And this we use, basically kept the output away, but so basically we have our parameters here, the 5,000 sample values. Now, again, with kind of the same kind of tool chain as yesterday, we can move and do a posteriori analysis. So here we have the first glimpse of our posterior distribution, which looks like a good first guess. So let's see what does if we do a network prediction. Then here this is much finer, so it's already getting better there. And we can even basically with very simple moves basically animate it, where basically it iteratively just moves around and shows how it keeps adjusting its barriers and its boundaries. There we go. So yeah, let's move to, let's basically view what we had up here. So basically, what did we have up here actually? If we try to summarize it for ourselves. So we basically had up here, we defined ourselves a neural network, a very simple one, which is fully connected layers. For Bayesian neural network, we basically needed to have an unpack function, which is basically hand-coded at this stage. And this one was basically needed to then be able to pull in the neural network parameters as priors, and basically then construct this probabilistic model, where you basically now you need this, you kind of need the, if you want to make it more efficient, and you have higher order probability language, programming language support. So basically you have to have recursivity. And just for the define our hyperparameters. And now we basically try to move to a case where this unpacking function, which we had before as well, so it's kind of like a, it's more like a boilerplate code in a sense. You want to express it in such a way that it's slightly more generalized. So you don't need to custom write an unpack function every single time that you want to run a different Bayesian neural network. So in here, we do the whole operation is kind of vectorized in a sense, which works a lot quicker. Then in here, we generate our neural network. We still have to unpack, but it's all vectorized now, so you don't need to write omega 1, omega 2, omega 3, etc. And for every index and network shape, you basically construct a dense layer. So again, this only works if you have one type of layer, of course. And then in the end, you chain everything and return it. And here, again, you basically have the same thing as before. We had our prior was defined from multivariate normal. We still define our prior from a multivariate normal. And then we use the neural network model to move the model forward. Then we use Bernoulli to access whether we should keep it or not. This is the way back end here. Should be fine. Yeah, it's quick. So now let's again use Hamiltonian Monte Carlo to sample from it. This time I think it's a few more samples, but should hopefully be fairly quick. We just probably go through it quite quickly in a second. But basically, in here and again, we want to do a statistical analysis on it to understand our results better. And again, basically taking the network shape, and then you want to basically plot the posterior. Yeah, and here we go. Which looks quite good, to be honest. You really can see that here that the red points are really well captured inside of the domain. The splitting between domains is done quite well. So that looks really good. So the question I posed to you in a sense is that basically when I did this with some students at uni, basically I asked them like, okay, so how do you expect the inference engine the scale and which inference engine should be the best. You always end up with different answers in a sense. And in here, I think the cutting short to the answer in a sense is that if you would have much higher dimensions, then variation inference might be the better inference algorithm. But for these low dimensions that we have so far, this is all working. So Hamilton Monte Carlo is always a very solid choice. But once you realize that Hamilton Monte Carlo hits a limit, then always a good first resort should be for you to just say, hey, let's try out what happens if I use variation inference, like normal stochastic variation inference or something like ADV or BBVI. So the next example I want to go over is basically, so Julia has a lot of push in the past 2 years using differential equations or in terms of scientific computing. And I want you guys to basically go through this, but at the same time think of it, okay, so which kind of API or which kind of functionality is differential equations exposing to the programming system at the same time to be able to exchange gradients and basically do optimization there, or basically also do statistical analysis. And that's then really important for us in a sense, because that kind of goes to show what you need if you want to link your own simulator or your own data generator. It doesn't need to be a simulator, it could also just be, it could be a sensor, even that wouldn't make a difference, or a camera. All of this could be your data input, but again, you need to think of the kind of data, the kind of additional data information and the kind of API that you provide to the system. And these simple examples are really good to show that. So let's just... So differential equations is one of the main flagship packages. So there's also this package called diffxflux. Basically, it connects differential equations in all kinds of manners, stiff, so ODEs, SDEs, delay differential equations. I haven't really used those, to be honest, but for PDEs and SDEs works quite well. And you can basically just what's most colloquially known as neural ordinary differential equations. They kind of construct that for all these different classes. So if you're really interested in that, I encourage you to really have a look at it. The documentation is really good. And the packages are also very stable and very well maintained. Oh, there's a typo again. So again, we basically import ourselves some statistical fancy packages, which we can use later on. And here we basically have a system of two differential equations which are coupled together. So yeah, this is just fancy syntax in the sense where you basically, if you press tab, it changes to the Greek letters. But if you write a repo, it's usually discouraged. Okay, so we have our differential equation here. We define our initial data basically. Then again, just like with Turing in a sense, we basically tell to differential equations, hey, we have a problem, we have an ODE problem here, which we would really like to solve. We give it the our function for the coupled differential equation. The initial data is empty, of course. The kind of range that we're after. Then we tell, hey, just solve it. Where TSIT5 is one of the normal ODE solving algorithms, but you can find more of that in the differential equations. And you just want to plot it, basically. And here we're basically looking at the two trajectories evolving. It all looks pretty normal. So now let's generate ourselves some more data. And now let's combine this idea of having this differential equation as a model with Bayesian analysis, basically, or especially Turing as a probabilistic programming system. So now there's this package which already brings part of the functionality that we need to have to combine it with Bayesian analysis. Basically, here we now basically give our priors over the initial parameters, and then we can basically use Turing for inference on the model to get a more Bayesian analysis of it. Right, I'll jump back once it has changed the plot, but I don't think it makes sense to just wait for it. But it should in theory be quite quick. It's always the presentation effect. But so now, in Tree, you can just combine different packages, usually pretty seamlessly. So what we now do is basically just try to use as much of Turing as possible. Basically then compose the differential equations inside. So now we use the for differentiation, define our self-Lotka-Volterra equation again, give it as an ODE problem, so define it to differential equations, and then have it be solved using the normal default inference algorithm here. Then we have our data. Basically, then so this here defines a probabilistic model that Turing views as a probabilistic model. Then again, it addresses it as a probabilistic model again, takes the data, and then basically runs inference on this. So basically giving the first glimpse of something that we need to think of if we want to couple our own data sources here. Differential equations has its own backend, basically an AD. So we basically get our derivatives pretty much automatically in here, which is something that we have to consider if we want to use our own data sources. We have to also be able to somehow get what some would say is a gradient tape. But if we have access to that, we can also do sensitivity analysis with that. I'll probably give a rundown of the different approaches to sensitivity analysis, given out of differential equations in a second. But adjoints, yeah, always the key concepts. We had it yesterday in the beginning, how adjoints are literally at the core of computing any kinds of derivatives inside of Turing, and it's the same here. Again, we have this wide compatibility, but I'll show an example in a second where basically I tried out with all of them and played around with it, but it still doesn't converge reliably. So you can end up in cases where basically you want to basically go back down to the simplest magnification backend and then see how far this can go. So basically here, more than 100 parameters is where you get better and better performance. Below that, it gets a bit more difficult to get good performance. So in here now we have still a reverse diff. So this is kind of the most simplest one. This is pretty much the same model definition as above. And here it tries to run, and in here it still works. So we end up with our summary statistics of our model parameters. And so this is, again, where it gets interesting now. So this is all the sensitivities and capability that differential equations exposes to us. We have basically do this forward sensitivity analysis, discrete forward. We need to have discrete problem, of course. Right now we use interpolating adjoint, which is kind of like a normal adjoint in a sense, where you basically still use the forward solution. So that could be something that you can usually also do in most of the normal solvers. And if you use something like sundials, for example, which is an ODE and PE solver package inside of your code, then you can also get a gradient tape from there, for example. And then you have specific adjoints for different differentiation backends. So now you want to look at the sensitivities here. I executed in the past already, so I will just leave it here as this one seems to be running. So again, you basically analyze it, and then you again end up with summary statistics. But it gets more and more interesting if you introduce more stochasticity. So that's where basic programming really begins to shine. So in here now you define a model where you basically inject artificial noise. So there's a version of the Lotka-Volterra equation, which is basically a stochastic differential equation. And the way you do is you discretize it, and then you can write it down in this form that they have here. And this is exactly what I do. You basically here, you discretize it, put it in, and then you put it into the defined as an SE problem. And then you get a lot more interesting statistics because obviously it has a lot more stochasticity inside. So the probabilistic program or probabilistic model becomes a lot more expressive. Yeah, this is stuck. I'll just quickly restart the kernel because the plots are, it's really interesting to see about the way you. So to my defense, this worked yesterday actually. So I tried it out and it worked, but apparently not today. So ODE data, defect base, that was the one that didn't work. Let's just jump through everything. And here we have our more stochastic problem. And then here we want to really have a look at the way stochasticity affects our view of the problem. Run. Yes, and while this still runs, just also let it plot that. And here we can get the means over the trajectories. And this is now here what I was alluding to earlier. So this is still the same Lotka-Volterra basically model fitting. Again, the SDE. Basically doing ensemble sampling, which is all fine. But here, the numerical solution is unstable. So you can really try it a great many number of times, but you only get results a few times. And it's more of a hit and miss. And while this looks like a lot of garbage, let's say, kind of gives you somewhere it gave the hint that the numerical solution is unstable. Yeah, there's so either the model is misspecified, it's not, or the true solution is unstable. In this case, the true solution is unstable. Is it progressing? Great. So this is now the main question that I want you guys to think about, which is the main point to consider here. The differential equations can be should be abstracted. In this case, it's a very simple example of providing some kind of different generative function. And now what we should consider is what does it provide, and what can we learn from that for the problems that we are interested in. So this case here, of course, the gradient tape is the most important one. But looking at the code, you can really look at the code and see what it's basically exchanged. And if we can provide that for a simulator, then we can just directly plug in our simulators. So that works usually quite well. This is again coming to this question of which interfaces do you really need, and automatic differentiation can be a bit of a problem sometimes. So with these more, let's say, legacy codes, you wouldn't really have access to derivatives. So you'd rather have to rely on something which is more sampling based. Let's have a quick look whether this is progressing in any fashion or whether it's hopeless. Kind of hopeless, I suppose. Yeah, it worked yesterday, to my defense. It should work on your own machine. For the sake of time, I would probably now switch to the remaining presentation so we can progress, because we also have a second notebook that I wanted to go through with you guys. So yeah, please excuse me kind of jumping ship here, but I think for all of us it's moving content along is probably a bit more interesting. Is that the right one? Here we go. Okay, so to summarize, our first basically touch with Bayesian deep learning. Posteriors can be really difficult, especially with our current sampling or observation-based algorithms. The only real way you can basically make the posteriors tractable there is you move to if you move to approximate Bayesian inference, but okay, I left it out of the inference algorithms overview because that would have stretched a lot further, and I thought that just basically constraining ourselves to the let's say normal algorithms at first would be best. Yeah, but basically because we're also parameterizing all these distributions of our weights, we have tons of parameters in there, so the sampling space becomes really quite difficult if you want to sample from the whole space. Data sets can be really large, and at the same time, multivariate normal is kind of just like a best guess what a good prior might be. So the right priors are really hard to find, where you might again end up with something where you say, okay, if I want to actively use it, doing something like the, I think it's from Michaelis Tsitsias paper, where basically they first introduced the split between first doing a few Monte Carlo estimations and then moving to variable inference. You can kind of do the same here. You could do a few raw Monte Carlo estimation runs, or just like a few samples, and basically then try to get an answer for what your best initialization might be. And then with that initialization, you could then actually start the algorithm. So let's move to part 2. So I think from the beginning, the idea for a lot of people behind it was clear that basically you kind of want to play around with these building blocks. You want to have these statistical building blocks, you want to have these network building blocks, you want to play around with them and basically put them together into something which is new, or basically pushes your imagination bounds, basically. So for that, here we'll go through GANs and VAEs. In between, we'll move to a second notebook where we'll basically it's not a working notebook in that sense, but basically it sketches the ideas how you could integrate it with your probabilistic program, and how you can basically jump between the two paradigms. And okay, so now the way we'll start is we'll first basically jump in and basically actually define for ourselves what would for ourselves be a type 2 system. So type 2, as Joshua Bencher defines it, so system 1 is what we currently have, these deep neural networks. They don't really have consciousness, they don't use any sort of linguistical features, basically, because they basically learn from the raw data. They're quite intuitive and fast, but again, then type 2 promises this linguistical structure. So that means that you could also combine knowledge. You want to have a reasoning component in there, and then also the conscious one is a big one, where basically consciousness is sometimes kind of compared to like these memory mechanisms or attention mechanisms. But those would just be the start. The main idea of consciousness in an algorithm goes much further. But there's, I'm not aware of a really big push there which really pushed the field forward yet. So the key for a level 2 system would be to try to move to this higher level semantic concept. And then you also want to combinatorially combine knowledge, or basically combinatorially also be able to combine outputs from statistical structures or deep learning structures. So the target here is kind of like a who's who of what the current models are starting with. So out of distribution generalization is always a big one. Just basically jumping back to the inference compilation from yesterday, where you basically have this in the inference loop, you have the number of LSTM cores which embeddings are attached. And then if you think of it, and it basically constructs a response surface for the actual function to sample from. But it basically means that the response surface is defined well on an isolated area. And as soon as you move outside, you don't really have any guarantees anymore, which is why, for example, Gaussian processes are quite well liked for these kind of surrogate applications, because they give you a really clear bound. What happens if you move, let's say, two centimeters to the, or 2 points outside of the domain that you've actually sampled from? You still have bounds of the maximum uncertainty there. Out of distribution transfer, again, you learn on a distribution, and you basically want to have generalized also, or transfer it to something completely different. Compositionality, I think on that end, we already saw what Dreamcoder can do, and that shows signs of compositionality, but it's not really a full system yet. So it's basically just a glimpse of these potential capabilities in that direction. Causality, generally a big buzzword right now to find causal structures. Knowledge seeking, that basically goes towards the conscious. We have this inherent curiosity backed into your algorithm or into your agent. Again, especially with agents, being able to find or define better world models would be really helpful there. So the key ingredients that you want to play with are attention. sparse factor graphs. Method learning is a big one. And also causal discovery. Attention is a really big one, which has permeated a lot of subfields by now. And it's really, so there exist many types of attention mechanisms, but in general, they seem to work really well. So with a lot of these papers from 2 or 3 years ago, you just saw basically, as you will see in the GAN paper in a few moments, where basically you just put in this attention mechanism, and that's basically the paper contribution in a sense, even though it's a bit of a cynical paper description. So yeah, generative models are one of these, basically a building block which we want to introduce into our arsenal of algorithms that we can play with. You can use them to construct oracles or surrogates, so oracles which try to predict the future, or surrogates which just to inference on to get to basically accelerate your inference machine as well. So going through GANs and VAEs. So with GANs, we'll first go a bit through the theory, go few of the more important models right now. And then we'll have a look in the notebook, basically how you can actually incorporate it in a kind of a code sketch, basically, it's actually the code. Then with the VAE, it's kind of same again. First, a bit of theory. It's a bit shorter there because the VAE theory is not, especially given that we've already covered variational inference, there's not a great deal of new ideas there. Of course, the variational autoencoder structure, as I will explain a bit, is the main contribution here, but we have already talked about variational inference, so we kind of already have half the rent there. And then again, a sketch of how you can usefully embed those in the POSIX programming system. So again, basically it's this core idea of basically you want to learn a model of the true underlying data distribution just from sampling from it. Then implicit model. You want to learn implicit distribution. GANs always have this 2-player min-max game where basically you have a generator and a discriminator which compete. The generator always wants to generate new data just from usually on normal GAN, you just from noise in the beginning and upsampling. A conditional GAN is where you would basically have more problem-specific inputs as well. But yeah, they try to compete. That's why it's kind of like an adversarial procedure. Generator, again, as realistic data as possible, which can be quite difficult, especially if you have very sparse rewards. And this is basically a bilateral optimization problem. So this kind of encapsulates the structure. So we have the real samples from a real data source or model here, and the generator also gets its most often it's noise vector here, samples up, and then they basically try to convince the discriminator which one is correct. So here's this bilateral optimization. You basically try to the discriminator tries to maximize its rewards, and while the generator tries to minimize. So that this is basically this game that's going on. This is still the original algorithm where basically you have a mini batch, you sample from prior examples, then you have a discriminator, so you have a stochastic gradient ascent on the one side, and you have stochastic gradient descent on the other side. So some people would also call this kind of like a divergence minimization because you try to minimize the distance. But in practice, it's generally established now that they don't do divergence minimization. So you learn the distance between two models and the model distribution. And they then provide the learning signal to your model, which should also give you the gradient feedback that you need to keep training your model. So if your distribution is optimal, yes, it would be really good and everything would work directly, but your discriminator is never optimal. And also you lack the computational resources to really go through the true data distribution. So basically you have to rely again on kind of like an approximation, but again, you partially you have to generate samples. And here again, you're dependent on basically the support of the distributions overlapping it. Otherwise, you can't really approximate. You wouldn't really get a sensible distance between two distributions. There exists a whole load of divergences in literature. So one of them is, for example, Wasserstein. It's I guess one of the most famous ones. The Wasserstein GAN, that was really big a few years ago. It's still a really big area. And then again, the Wasserstein distance becomes computationally intractable for complex cases. This is again where if you want to incorporate it as a building block, you really need to watch out for how difficult the model actually is. But the inference will be tractable there. Another alternative here is small matching distributions. Then F divergence, this is probably the most general one. So they define their own variation lower bound. With that, they have one more constraint, and you can kind of combine it to define the F-GAN. So summarizing the whole GAN part up to this point. So a GAN provides really good samples when it's probably trained and has enough data. Has a good learned loss function, but it can be very hard to analyze, and convergence is not guaranteed. They can be really hard to train, and you might need a lot of hyperparameter optimization, hyperparameter tuning. Divergence minimization, yes, it gives you optimal convergence guarantees. It's easy to analyze, but then again, it's very hard to get good samples. And yeah, if you evaluate it in the human fashion, you would end up with most often different results, which is not great. So now moving more to the science angle now. So basically then you have to begin to consider the difference between unconditional and conditional GANs. Conditional GANs have a much clearer connection to the physical domain, or like a more science domain, like natural science domain, where you do have some signal, and you can provide as input, and that usually already improves your results by quite a bit. And again, people already use them to define physical constraints. There are also some papers where they basically try to approximate incompressible fluid flows just from fluids data. So let's move to the what you call model zoo, I guess. So this is the traditional conditional GAN. And what you kind of do is you provide some information on top, like in here, because it's an image, obviously tags, and then you end up with a much better description for your problem. It works the same way for physical problems. You give some problem-specific information as initial input, and the network can already do a lot more with that. Deep convolutional GANs. We'll use deep conv GANs as our example in the notebook, but also what they're really interesting for is this notion of a start of first glimpses of compositionality. So it's basically trained on this massive distribution of, I think, celebrity images or something like that. It's images, but I'm not sure if also have to be celebrities. It's basically able to begin to reason about them. So say, if you have a smiling woman minus a neutral looking woman plus a neutral looking man, you end up with a smiling man. The same thing exists for people with sunglasses or very different haircuts, for example. So this is where they began to introduce self-attention. So basically you just can use it to just capture structure coherence, and they do that in this case here to basically capture it from the images themselves. And this was the first time attention was introduced, as far as I'm aware. There might be something earlier. So Logan basically works by latent space optimization, where they take gradients on latent space and hence improve that a lot. So basically improve the movement on latent space, and that when transformed back into the image space results in much better pictures. So if you, for example, if you look here, this seems to be kind of off in a sense. Whereas here, all the images look pretty accurate. You wouldn't really be able to go from here and say, okay, this is not done, let's say, Africa, or for example, or sorry, of the animals in natural habitat. You would really struggle sometimes to really see that they are artificially introduced into the scenery. And also it has a lot more variety in terms of the samples it generates, but that's also coming from them having a lot more data. So as I said before, the response surface that they have is a lot bigger. So again, you would directly end up with a lot more variety there. Progressive GANs, they basically start with a very small one, let's say 16 for us right now. Then you do this kind of like an upsampling where you introduce a 32x32 layer. And then at some point you phase out the 16 with some 16 and just throw it away. And you basically end up with having these images and the 32x32, and that kind of keeps going until you basically hit the, I guess, 4K would probably be the solution these days. Infogans, they basically introduce an inference network to solve the inverse problem, given the generator output, and basically it begins to associate labels with each category, which make results a lot more expressive and provide a lot more interesting outcomes. So means so far all the GANs that we've covered, you could theoretically consider to introduce into your POSIX programming system. Maybe not big, not the big one, because that's a bit more difficult. Pix to Pix, I think that's was, I'm not sure if I showed it, but it was already used by Dustin Tran and Edward June, for example, where it just imports it and basically can then do a POSIX analysis on a model. But it's really interesting basically to reconstruct those images. There was quite a lot of work in the past few years on using this reconstruction of images from satellite data, especially in terms of like climate science. There was a lot of movement behind that. Yeah. So here they basically, you want to look at videos, and basically you have to still capture correlations, but cope with all the frames that come in quite quick succession. And here the whole approach of Papertech is basically they first analyzed it, and then they improved the recurrent unit to then get even better results. Gale is basically generative imitation learning. So basically you want to be able to imitate certain behaviors in a reinforcement learning setting. So you can kind of do model-based reinforcement learning while still benefiting from some bit more sample efficiency. Then Spiral as the last system here in this stage is again something which goes more in the direction of Dreamcoder, where you basically want to take, for example, images or code or other structures, you want the algorithm to write new ones. And here, so you basically have to kind of enroll your execution traces. Then you have distributed training running on the algorithm. Again, in a sense, you could say this is the generator and this is the discriminator. And that kind of then pulls it everything together. And with that, they're able to achieve these quite impressive results where basically the machine can redraw from very minor dips and dots that you do on a page of paper. So let's move to the second Jupyter notebook. I think, yeah, I think we're good on time. Let's quickly. Here. All right, I think this notebook should also already be online in the GitHub. So here, basically, we start here everything with the normal stuff, the boilerplate code, to basically get a structure for hyperparameters in Flux. And because we would want to work with MNIST, you have to provide some boilerplate code to basically create output images. And then you basically can directly move into this inclusion stage, where basically we define a deep conf discriminator and a generator. The loss function is still normal. Everything is still pretty normal. You provide the training code for both, and everything is pulled together into one large training routine. So this would be the normal flow we would go in Flux. So the first option would be to introduce it as to basically construct the Bayesian GAN. There exists some work on that. I think there's a paper some years back where they basically tried that out. And as with many papers, it worked well for some cases and not so well for others. So in here, again, you have to make the neural network more flexible to really take in the neural network parameters once you put that into the function. So this is the main difference here, that you basically now you have to provide the neural network parameters, and most of these hyperparameters on the right-hand side will go away for this more automated way of taking up the hyperparameters. So this is also more of a sketch, to be honest. So again, hyperparameters here, but basically, so okay, you have looking at the discriminator, for example, you basically, again, you sample the prior from multivariate normal, and then you pull it through the uniform forward model. The same thing goes for the generator. But what is not contained here is the full training routine where both of them would be combined back together. The other option would be, for inference, you construct a third model, and this would then inherit from the two probabilistic models below, which is supported in higher order probabilistic programming language. Inference might be quite hard, but using some tricks or using stuff like approximate Bayesian inference, it should be tractable. The second option then is if you just consider the inference compilation work, you could do the same thing for GAN, but GAN would not really satisfy the constraint that you want it to be automated in a fashion, because you would have to train it first, in a sense, with your data. And then you can basically use the train generator to then be your data generator in the future. So here the main difference is, again, that you basically, in a normal sampling routine, you would basically now sample from the space of models. And the rest is pretty much standard boilerplate code. So an interesting third option, which is also the most involved in terms of if you would actually code it out and make it work, would be to abstract the whole GAN as a probabilistic program. It's obviously incurs a bit of a syntactical overhead, and you need to be aware of the problems that might introduce, like basically, again, being stuck in like nested sampling routines, or having too complex of a stochastic control flow as well. But it can free you from a lot of constraints, so it's really interesting in that regard as well. So again, you first define your generator, which is pretty normal here. But now what we want to see is we look at this and we can basically make out code blocks that we would want to define as custom structures in the spirit of the introduction, where basically you have these custom distributions. And so this is the multinomial, this is provisional, but you need to find the distributions you think are really representative for that muscle group, basically, of for that group of networks. And then you have to provide a certain set of API functionality, distributions, and also what's left out here is the bijection. And then you can basically, you end up with this. It's like, I call it an unshackled generator, where basically all the constraints from the generator are removed. And you can just play around with it. So let's move back for the variation autoencoder section. So what are VAEs? So basically you, in a nutshell, they are generative models with continuous latent variables. You parameterize the likelihood in the posterior with neural networks. If you parameterize them, they usually tend to be prior inversion posterior. They tend to be Gaussians. And then there's this massive trick at the core of variation autoencoders, which allows you to transform your loss function into something which moves from intractable to really highly tractable. So there's currently, I think it's still under review, but there's this review on variation autoencoders. It's a really good read. I can really recommend it. Okay, so for binary data, you would have a Bernoulli in the decoder. Prior normal again, real valued, you would have just the neural networks. And then the variation posterior is again decoded and has again these neural networks behind. So especially in this scenario, something like attention mechanisms would be really interesting. So if you want to try out, that would be something that could be quite interesting. It could provide some really interesting results, especially considering that there exist so many different types of attention that you could possibly use here. So this is now the reparameterization trick. So in here, you basically introduce this noise, which makes Z at that point then by transformation deterministic, and then you can compute a backdrop. That's the main idea. So as you can see here, so in here, Z was still random nodes. You couldn't really propagate over it or take derivatives through it. In here, you basically move that away, and that allows you to basically just take off gradients. So they're trained in the same way as variation inference algorithms. They use the elbow. The positive part, as we'll see on the next slide, basically gives the quality of the model's prediction through construction. So basically construction error, and the second part then is basically like a regularization. In a sense, some people say it's also a measure for information about the observations in latent variables. So in terms of theory, so it has gotten a lot less restrictive since its inception. Basically, the structure of encoder and decoder even now gets mostly taken for being variation autoencoders. And there exist many extensions, of course. It's a highly active array resource. So you could have multiple latent layers, non-Gaussian latent variables, non-Gaussian posteriors, inverse autoregressive flows, mixtures, autoregressive structures, use ResNets or GraphNets, for example, in your decoder. And again, there's always this backdrop again of further and further improving what has inference algorithms, which again make inference a lot more tractable. It's a really interesting application, I think, that came up, especially that people started using it for chemical design. Or I think it's, sorry. So this is chemical design. The other one was just, so it's just the inverse autoregressive flow. If you want to have more of a flow model, but this is the interesting one. So basically you have this discrete structure, you compose everything down to like this molecular level. You can propagate back out and gain insight into the structures. So that's really interesting. So let's go through a few example version autoencoders. So the first one is, I think, from ICLR this year. So basically, the mixed curvature basically means that you can convert the normal curvature that you usually deal with onto, more like a ball in a sense. And then you can train the VAE on this curved space. And you can also argue about generalization on that space. So the reason why this paper, for example, was so extensive is that they had to redo a lot of the math that you usually just presume to be satisfied, and they had to rederive everything. So this is something I find quite interesting, which is also, I think, would be really interesting for anyone here that's interested in kind of like the engineering physics kind of side. So Cool DeepMind came up with a new model where basically it's kind of a VAE, and the contents is kind of combined with this. Sorry, lost track there. Yeah, so sorry. So it takes in image sequences. Then by respecting the Hamiltonian constraints on the phase and momentum, it can basically extract the Hamiltonian structures. So in here, normally they would just use it to propagate the system forward. And in that way, they can, of course, take a loss. Say, if you propagate the system by 10 time steps forward and see how well it still performs or how accurate it still is. But also there exists a way to modify it. And then you end up with something which is also really interesting. We have Hamiltonian flows, which you can, I mean, normalizing flows are quite big. So having a Hamiltonian structure opens interesting new possibilities, but I must confess to have not be completely up to date on that corner of the research right now. Information maximizing ones, they basically replace the training objective with the elbow and say, okay, the elbow usually neglects a lot of the latent variables. Our information theory approach can be a lot more efficient, and that's why they basically replace it with that model. Different one is always hierarchical models. So I don't think I've touched too much on that yet in the course. But if you look at the structure and if you kind of followed, let's say, some of the recent crazy advances in transform modeling, then you can really see that some of that comes from the idea of conditional computing, or basically, again, introducing communication primitives into what is then called a sparse mixture of experts. And what they do in here is they basically construct a mixture of experts layer for different instances, and they can then work together, basically. Then again, you reduce the problem down to many more smaller pieces. So it can work well, but it can also work backwards. So let's move to the Jupyter notebook. Any questions already? Okay. So as with the GAN before, you have to write down a lot of the supporting boilerplate code. But then again, this is just basically defining the structures and defining the encoder and decoder. Model laws will always stay the same. So now what we need to do is here, what we first need to do in practical also is that we need to define variational models for both of them, where in here the decoder is part of the decoding from the latent noise, and in here takes it in. So training routine for this kind of a setup would then look like this. So basically the core is again, in here, you use variational inference. So first you have to initialize your variational inference algorithm. And then you just have to basically run with it in here. Where basically you compute the variational inference of it, and then you take out the alpha from that. So I know the sketches were quite short, but I think in terms of the basic ideas behind it, it should hopefully make it a bit more clear, especially if you want to have another look at the code. So I think we're about 15 minutes ahead of time. I'm not entirely sure what you want to do. Please let me know. I don't see any questions in the Slido yet, to be honest. And there's also no one in the chat writing anything. So please let me know what you think, or what's your preference is. Do you want to do it? Shall we just continue? So lecture 4 was initially thought of as a buffer, so it's not a very long one. So we could, if you want to, we can pull it ahead and basically do the whole lecture. And there should be like, should be about maybe half an hour to 40 minutes, I think. Whatever works best for you. I'm completely open to your suggestions. So I guess if so, maybe then I would suggest that we reconvene at 12, if that's okay for you guys. So it's in 45 minutes. And then we'll do the last lecture there, if that's okay for you guys. I see Roman typing, so I'll wait for him. And okay, if you want to go on, then sure, you can just finish it off right now as well if you want to. So so far I've mostly been going through the systems and the building blocks. And something which I really wanted to give you an insight to, and which I have been spending a lot of time on, is basically how you construct these systems at scale. Talking in terms of like supercomputing scale. I really just need to open the right slides, but all right. So let's switch to share. All right. I think presentation mode. Okay, so this is mostly about what do you have to think about when you construct such a system, or when you draw up a system at scale for something that you're considering. So let's start. So this is now becomes more of an engineering challenge. And so the tools I'm mentioning here are what I consider, or from my experience so far, are kind of like the best tools to ensure a certain number of pragmatic considerations for you to be able to repeatedly do your application and basically validate your results, or also really scale up. And scale up is always a big problem in here, partially. So the real challenge here is, if you do hundreds of thousands, hundreds of millions of simulations, then managing the data, even if the data itself might just be a few kilobytes, which it's usually not, but let's just assume it's a few kilobytes, you still need to keep track of those basically 100 million particles moving around on this large compute cluster. So what you really have to begin to consider is data movement, the maximum amount of data that you have in there, concurrent processes might be prone to crashing. It's a common problem of these large supercomputers that sometimes just servers just disappear or the network just has a glitch. I don't think it's a secret. So a lot of the times usually, a lot of the computers usually have at least one, let's say, incidents a month, which is quite normal. But those systems really try to push the performance. So that's kind of the trade-off you're making there. And then also what you really want to consider is how can I port my application? If let's say I construct this really giant model where I draw together this, let's say, a user transformer model to basically do an attention-based oracle. And I really want to use that to push my model forward. So it means I have, what do I have? I have the transformer, which obviously is a huge model. So it has to be to fit somewhere in memory or somewhere into the system. So, and also you have to have your simulator. So you need to be able to generate a lot of samples. And then you have the statistical analysis code and the Bayesian inference code. So all of those together are quite difficult to place. There exists some interesting stuff in terms of where they did for chip placement, but they also used a sparse mixture of experts layer. And basically with that, they determined where to place certain logic chips for semiconductor on a chip. And some people tried it out for supercomputers and it worked surprisingly well, actually. It's quite expensive, but probably in 5 to 10 years, we'll have allocation of supercomputers done by reinforcement learning algorithms. So this is basically where the Probabilistic programming basically begins to switch in terms of its structure, in terms of what you basically try to phrase it in terms of an HPC engineering problem, so that you can kind of understand the application effects. And usually if you talk to the HPC guy, the actual guys at the computing center, they want to say like, hey, I have this and this memory bandwidth, I have this and this utilization of this many cores, my application scales like this. And that's usually how they try to determine if you are actually a suitable user for the machine, if you could actually utilize the hardware. But in this case, parallelism is usually not an issue because we basically, because we sample so much, we have a model-based parallelism, which means you have tons of models which are independently running on a system. So in that sense, you're not limited. You're basically just limited by the amount of compute you can get at one point of time. And kind of the advantage coming out of this area is that basically by making it much more efficient on these massive machines for these very large amounts of data, it also means that if you update your software to the newest system, where basically it has some of the patches in the Probabilistic programming system, it will run more efficient as well, because obviously all the performance optimizations go into the next release usually. So this is probably one of the core tools, especially, so they mostly initially used it for like human brain simulations because they wanted to do hundreds of millions of simulations and trajectories. But it has been shown to be a massive boost for machine learning, especially in conjunction with scientific simulators and HPC. So basically at this point now you can, they've tried out for up to 100 million simulations and managed them simultaneously. And you can break it down to batches in traditional sense. But in theory, you could run up to 100 million simulations in parallel, which is a humongous number and where you usually use track, but Merlin has a few extra traits inherent to it, which allow to really keep track of all the individual simulations, know where they are, what their status is, when you can expect to get data back, and what it has to do, for example, if something crashes. So if a simulation crashes in a classical sense, if you say you have some container and it crashes on some remote machine, it would just directly reschedule the container somewhere else. And so you wouldn't really need to worry about this. So in the past with HPC systems, you usually need to do it by hand yourself, but now it's all automated. And so the software can actually scale over multiple supercomputers. So they could be in remote locations as well. And you could throw in cloud components, but also it can be made hardware aware in a sense that it knows where do I get CPUs, where do I get GPUs, TPUs maybe, FPGAs, how can I allocate the calculations most efficiently. And that works actually quite well. And I mean, they tried it out on, I think this now the third biggest machine right now. So of course it will work quite well if it can scale to the whole machine on there. You can always have a look if there's spare capacity available and just schedule more runs. With that, you can kind of just keep the whole Merlin job running for weeks, and we'll just at some point say, hey, I'm done. It's persistent. So basically Merlin has one control server, as you will see in a sec, which basically keeps track of everything. And as long as that server doesn't fail, it can indicate anything else. It's kind of like a microservice. So this is what Merlin usually looks like. So you have, you sit on your workstation or your laptop mostly these days. You describe your workflow, and for that, as you'll see in a second, you basically use this. You have to express your workflow as a directed acyclic graph. Anything you can express in that graph is possible. So this is the kind of syntactical boundaries you're dealing with in Merlin. But basically, it has this server which basically acts like a database and then schedules GPU allocations. So basically, if you do, let's say, training, or if you do inference, you can move the inference to CPU machines and coordinate all those tasks. Maestro is just one of the cluster managers or the cluster schedules that Lawrence Lenovo offers. So it can do asynchronous task queuing, so it doesn't need to do everything at the same time. Can manage the queue dynamically as well. That's through one of the Celery backends. The central workflow file is the DAG that I just showed, this one. This basically describes the whole workflow. RabbitMQ is the database running in the background, which basically keeps track that everything that you specify is actually running and is moving along. And Redis is basically a backend so that everything can scale up to these hundreds of millions of simulations. And what has to be said is the 100 million that has been shown so far is only because you could only get allocation for 100 million. It doesn't mean that it stops scaling there. It's model-based parallelism. It could probably scale to 1 billion if you would get enough allocation. So this is how it works. You have the scheduler, the dependency graph that you're providing. You provide all of those. Then RabbitMQ basically begins to talk to the machine and tries to schedule and get enough capacity. Once it runs, you have the worker, which is basically either, let's say, a server or a node with GPUs or CPUs running an instance of your code. And it either communicates back to the results database, but also, this is the interesting one, the message broker here is the one which protects you from losing A, files, or B, whole simulations. And if you're running this, like, let's say, a sequential one where you always throw batches at the system, you really need to make sure that all the sampling points selected by your Oracle are actually sampled. So that's, with that you have to move along. And if you lose samples there, it can really affect your inference routine adversely. So hence, RabbitMQ is an absolute godsend for that kind of problem. The second approach, how you could kind of do it, which kind of does slightly, it's phrased slightly differently because it comes from a different area, but it can do the same thing. And might actually be more, if you are used to TensorFlow or JAX as well, then Reverb might actually be easier for you to use. So Reverb basically just was intended as an experience replay platform. So because reinforcement learning, especially off policy and on policy, okay, overall reinforcement learning requires a huge amount of samples. you somehow need to manage those. And that can also become quite difficult. But again, as with the HPC one that I just mentioned earlier, you again have model-based parallelism, so everything is great as long as your individual application is running well. But still, you need to manage all those samples, manage all the data, manage the data communication, manage the data inflow into your machine learning system or your probabilistic programming system. So in here, VWeb is basically a bit more of a light touch approach. You basically just have tables which refer to data files. And if a file is not in the table, then it gets deleted. And that's what kind of approaches. So basically you have your, this would be deep Q networks. You basically have a reinforcement learning agent. You have to learn, and then in here you have all these different servers running it. Also the data. Sorry, this is where it's running, environment transition model, and gives the data back to the ReWeb server, which basically keeps track of where all the data is, and the learner keeps improving the model. But again, it's kind of the same. So you can absolutely, so I know some people who did it for TensorFlow, where they basically you can just hack it and basically make it do the same thing. And works out of the box. It's made to scale as well because DeepMind always has these massive problems where they want to generate tons of samples. So yeah, the system is custom made for them in a sense, or they made it for themselves, but in doing so, they made a system which can handle lots of data quite well, while not incurring too much of a performance penalty overhead. So now, moving a bit more, a little deeper, let's say, into the HPC end here. With these large simulations, you usually generate a lot of data. And the way you store this data and you process the data and move it around can usually make or break your approach. So in my case, my applications are always memory bound. That means that I could really, more memory bandwidth would really help, but I usually don't have it. So moving data in and out of memory is a huge boon. And with that, this is where Apache Arrow comes into play. So it was basically introduced as an open source project in 2015. So the guys who do it are basically some of them did pandas beforehand, and they realized that they incurred a lot of performance penalties over time in writing pandas. And they kind of wanted to correct that perception and basically build a new model. So this is where they moved along. And they basically said, okay, we'll build a completely new model to view data. And also basically disaggregated data format from the actual programming language. So the core is language agnostic, in C++ with performance, but the APIs are there. Which is really interesting. Not sure if any of you worked with it yet, but basically there's this framework called NVIDIA Rapids, which basically allows you to basically run kind of Python on GPUs in a performant fashion. And they use Apache Arrow as well as data format. Yeah, and so in here, basically in the past, you would have to connect everything between different frameworks like Pandas or Spark, for example. You would have to have all kinds of different transitions. And now everything is just basically, as long as it's an arrow, then you can just move the arrow object around and everyone will view it the same way. So that's really nice because it's also makes the data really reusable. Yeah, so basically in exchange, the serialization overhead is very small. CPU, GPU works quite well. Can handle multi CPUs, so multi-core architectures, simplify the whole thing a good bit. Data locality usually helps against these large memory movements, which clog up your high-performance network and then slow down the rest of your application. And parallel processing, of course, is kind of what you need these days. Compression, yes, sparseness is a bit more of a complex problem. But compression is already something which is quite prevalent. There's also, from the HPC side, there's also something called ZFP, which is has shown a lot of promise. I can just quickly switch to it. Let's just quickly switch to it. I hope it's interesting for some of you. So this is ZFP. And they're basically, they're able to compress floating point arrays into arrays. And because they can basically reduce the amount of data movement that you then incur on the system, they can really accelerate applications, especially memory-bound applications. And that's really, they have support for a lot of the normal HPC languages. Especially if you talk in terms of like traditional HPC or like the leadership style HPC, then you would probably still see Fortran codes. Because Fortran is still quite good for that. There are new languages coming up, but they tend to be more esoteric and not enter mainstream as much anymore. So you have these, there's a current one is called Chapel, which came out of a DARPA project. But yeah, those are really esoteric languages. You wouldn't really need them if you don't want to program one of these large systems. But yeah, memory compression and efficient memory management becomes more and more so important if you move around in these large systems. Especially, you always have to, some argue that the main performance of a supercomputer is not only in the hardware, but also in the network, because if the network is not able to support it, then of course you lose. But if the network really supports it, then really have a lot of advantages there. And from my point of view, which is really interesting, so Apache Arrow also has this platform called Apache Arrow Flight, which can basically handle continuous data streams. You basically fly them as services over the Google RPC API and avoids any copying or deserialization, has low-level optimization, everything, and you can actually scale this to very large-scale data streams, which also works for HPC actually. So this is what it kind of looks like. You have the data nodes you might simulate on there and then give data back, and you have the planner, and then you have the client, which basically manages the whole thing again. So in a sense, the pattern from Reverb and Merlin, where you basically always have to have one control server, which basically controls the whole thing, repeats. And this control server is always then your point of failure. Yeah. And here you can kind of see this, you can still optimize it a bit further if you know more about your data. But zero copy is quite good for HPC, and serialization, deserialization usually is the one which incurs the most performance penalty. So if you can avoid those at any cost, then you will get really good performance, which then means you can generate more samples, which means you have a better shot at actually having inference routine converge or running more expensive or more complex inference routines. And that can really then push your application forward, or the understanding of your application you're trying to gain. So the other thing that I want to touch upon, I think, especially because I think Roman brought it up yesterday, was with the ARM machines, and that's so the reason why I wouldn't really worry about it from this kind of view is that the kind of magic these days has moved down in a sense into the compiler backend. So just looking at TensorFlow here, for example, and we'll go into XLA in a second, but basically XLA provides this interface to all these accelerators. So if you have access to all these intermediate representations, so you can access a tons of hardware there without needing to worry about your portability. Yeah, so XLA was basically was brought up when they didn't really have an inkling of a real machine learning compiler yet. And initially, it was just improve execution speed, memory usage, and improve portability is a big thing, because even people like Google have loads of different servers, and you can't make sure that you always run the same kinds of servers, so you need to be able to port your application. And with that, you kind of move the magic down to the back end. And yeah, this is what kind of looks like. So you have XLA, HLO is the intermediate representation for this kind of compiler. You do some kind of analysis on the graph, and you basically subsume the kernels together to get much more efficient compute kernels. And then you basically generate the machine code and run it from there. And that kind of sums up the whole approach, basically. So basically, if you think in terms of data movement, which is a massive problem, Apache Arrow is a good shout out. And they're really beginning to hit their stride there. And we already use part of Apache Arrow for our applications. Amount of data, Apache Arrow and compression, the combination there is often necessary. Managing a very large number of processes, Merlin, and then portability, XLA. MLIR is just also from Google, but it's mostly in terms of LvM, which is one of the main compiler systems. It's intermediate representation of intermediate representations. It's kind of like like a super class. And the interesting bit here is that XLA is getting more new functionality, which is really well suited for HPC. It kind of looks a bit like they're trying to reinvent some of the old HPC typical approaches, like MPI, for example. So they had a recent paper which is called G-shard, where they scaled up to 600 billion parameters, and they had to use something which is called sharding, where they basically just just train certain parts of the network in the mix of experts at a point. And that is kind of now upstreamed into XLA, so that will also be available. So there's a lot of performance optimizations and new performance capabilities being moved into XLA, and hence being available to a user like you or me when we use, let's say, TensorFlow, PyTorch, also as an XLA backend, or JAX, for example, or Julia can also compile into XLA, and you basically just get the performance for free. And your application is portable. So you don't really need to worry about if the next computer at your university or where you work now is an ARM computer, or is an Intel computer, or an AMD computer, or which graphics card or accelerators in there. The compiler basically hides this abstraction layer away from you. Yeah, so thank you for your attention. I really had a lot of fun trying to bring as much of my knowledge across as possible. I was really hoping to see you guys in Lviv and actually basically sit together over some Jupyter notebooks and think through them together, which is, I think, quite a different process than me just basically going through the notebook that I wrote previously, and obviously probably being a bit too fast there. I really hope you enjoyed it. So if you have any questions, I'll be available in the chat, or I can also just look in the Slido, or if you have any further questions which you don't want to write in the chat, you can also always write me an email. I think the email is pretty publicly available on the web. I'm happy to answer as many questions as possible. Yeah, so thank you for your time. Thank you for your attention. And I hope you have a fantastic day, and maybe see you around at the conference at some point.
Thank you, Ludger. It was really amazing and such a great opportunity. Thank you for your lecture.
Thank you. Shall I stop the recording?
Yeah, I'll stop it now.